Welcome to the debate. Imagine for a second that you were holding two just absolutely flawless red rubies.
Right, deeply saturated, perfect color.
Exactly. Chemically speaking, they are twins. I mean, they bend light the exact same way, they feel identical to the touch, and they possess the same incredible hardness.
But there is always a but.
There is a big but, because then you slide them under a highly sensitive microscope, or you run them through a mass spectrometer. And deep inside the crystal lattice of the first ruby, you find this microscopic, ancient speck of iron.
Absorbed from the Earth's crust like millions of years ago.
Right. But inside the second ruby, you find a trace atom of industrial tungsten.
Ah.
Yeah, to the naked eye, they are identical. But one is worth tens of thousands of dollars, and the other, well, maybe a few hundred.
It's, it is the ultimate paradox of modern gemology. We have actually reached a point where human engineering can replicate the slow, totally chaotic magic of geology, and we can do it in a matter of hours.
And that brings us exactly to the profound central question we are unpacking today. So given that laboratory-grown gemstones replicate the primary chemical composition of their natural counterparts perfectly,
Flawlessly, even.
yeah, flawlessly, does their distinct trace element chemistry, that microscopic tungsten versus that ancient iron, does that make them fundamentally different materials, or are they exactly the same gemstone, just born in a different environment?
Right. It forces us to decide what actually makes a mineral species what it is. Is it the architectural blueprint, or is it the dirt the house was built in?
I love that. That frames the tension perfectly. And, well, just to lay my cards on the table here, I will argue that a gemstone is defined by its entire chemical reality, not just its primary blueprint.
Okay.
The unique trace element signatures we see in laboratory-grown stones, so both the physical intrusion of manufacturing artifacts and the stark, highly unnatural absence of geological impurities, those fundamentally distinguish them. They are completely separate chemical entities from mined gems.
See, I look at the exact same data from the source material and draw the complete opposite conclusion.
Naturally.
Of course. Because the core chemical structure is perfectly replicated through controlled crystallization, I argue that laboratory-grown gems are fundamentally the identical material to mine gems.
Even with the tungsten?
Even with the tungsten. The trace elements you are so focused on act merely as circumstantial environmental noise. They are clues to a birthplace, not definitional markers of a species.
Well, let's get right into the mechanics of that, because you are relying heavily on this idea of an identical primary chemical structure. But you can't just look at a chemical formula in a vacuum.
Why not? The math is the math.
Because you have to look at the violent, highly mechanical way we actually force these stones into existence. When we analyze the chemistry of laboratory-grown gems, we aren't just finding a lack of nature. We are finding the heavy, indelible footprint of industrial machinery.
Okay, but
We are finding crucible metals, right? Gold, platinum, iridium, tungsten, and molybdenum. We are finding furnace refractories like zirconium and yttrium.
right, but those are trace elements. We are talking about amounts measured in parts per million, or even parts per billion.
They are, sure, but their presence is a fundamental deviation from nature. Think about the heat required to melt these raw materials.
It's extreme.
It is so extreme that it slowly degrades the very machinery used to house the melt. The laboratory equipment physically sheds these heavy industrial metals directly into the crystal lattice of the growing stone.
A mine gem grows in a messy geological soup too.
Yes, but the extreme purity of the laboratory's raw materials, juxtaposed against the highly specific metallic artifacts of their machinery, it results in a gem that lacks the defining characteristic of natural geological processes. Because of these distinct, permanent chemical markers, I believe we are dealing with a completely divergent class of material.
Hold on. You are treating that microscopic trace of platinum or iridium like it's some sort of unnatural genetic mutation.
It is.
But the foundational architecture of the stone hasn't changed at all. To understand why these stones are identical, We just need to look at how nature builds a gem and how we replicate it. Take emeralds, for instance.
Okay, let's look at emeralds.
In nature, the Earth builds them using a highly complex, very specific recipe of beryllium, aluminum, silicon, and oxygen. The formula is Be3Al2Si6O18.
Right, that's the base structure.
Exactly. And in the lab, we use that exact same recipe. We do the same for rubies and sapphires, which are just crystalline forms of aluminum oxide, Al2O3.
Sure.
Spinel is a precise arrangement of magnesium, aluminum, and oxygen, MgAl2O4. Alexandrite relies on beryllium, aluminum, and oxygen, BeAl2O4. We aren't making approximations here. We aren't making plastics that just look like gems.
I never said they were plastic.
But you're calling them a divergent class of material. We are facilitating the exact identical molecular architectures found in nature. Even federal trade regulations support the structural reality.
You mean the Consumer Protection Guidelines?
Yes, the FTC. They mandate terms like laboratory-grown ruby or synthetic ruby. By legally requiring that the modifying prefix precedes the foundational gem name, they are validating that the end product is, structurally, a ruby.
I think that's a generous reading of consumer protection laws, but go on.
Whether the growth method is direct melt, solution growth, high pressure, high temperature, film deposition, or sublimation, every single one of these methods successfully replicates the natural crystallization process. Because that lattice is built perfectly, trace element differences like an atom of molybdenum are trivial edge cases.
I fundamentally disagree that they are trivial. And I think we need to look closer at the specific physical methods of creation you just listed. Because the manufacturing process intrinsically alters the gem's identity.
How so?
Let's take the direct melt growth methods. Things like the Zokashwalski method or flame fusion.
Oh, the Zokashwalski method is brilliant.
It is a marvel of engineering, absolutely. But let's explain what it actually is to the listeners. You have a glowing, superheated vat of liquid raw materials, often housed in an iridium crucible.
Right.
You lower a tiny seed crystal into this molten liquid, and you mechanically, constantly rotate it while slowly pulling it upward. The liquid crystallizes onto the seed as it cools. You are taking incredibly pure materials and forcing them to crystallize in a matter of hours or days.
And the result is a flawless crystal.
But if you think that's artificial, it gets even more complicated when we look at solution growth methods.
Ah, you're referring to flux-grown gems.
Exactly. When a gem, like, say, a synthetic spinel, is grown via the flux method, it doesn't just assemble its primary formula out of thin air. To grow a crystal in a lab without the millions of years and extreme crushing pressures of the Earth's crust, scientists have to cheat the system.
I wouldn't call it cheating.
They use a flux. This is essentially a chemical solvent made of heavy elements. Things like lithium, boron, fluorine, vanadium, lead, and bismuth.
Right. It lowers the melting point of the raw materials so they can crystallize at manageable temperatures. It's just efficiency.
Precisely. But they create a liquid heavy metal soup. And as the raw materials dissolve and then slowly crystallize out of that soup to form the gem, they trap those flux elements inside. They absorb the lead and the bismuth.
In very small amounts.
But those elements become inextricably trapped inside the growing crystal lattice. They become a permanent, artificial fingerprint of the laboratory. You cannot separate a flux-grown spinel from the lead and bismuth that birthed it. It is inherently a product of synthetic chemistry, not just a cloned structure.
I hear the intensity of your focus on those manufacturing impurities, I really do. But there is a deep, just philosophical inconsistency in how you are treating these trace elements.
Inconsistency?
Yes. You are framing laboratory impurities like a trace amount of platinum from a high-temperature crucible or bismuth from a flux as an alien artifact, a corruption of the stone's true identity.
Because it is. You won't find a natural ruby growing in a pool of industrial bismuth.
But geological processes also introduce a wide, chaotic, and totally messy range of impurities. When a natural gemstone absorbs a massive range of extraneous dirt from the earth, iron, titanium, chromium, we romanticize those elements. We call it part of its true identity.
Well,
Why is a trace amount of lab platinum a disqualifier, but geological iron from a dirty rock bed is a badge of authenticity.
Because one is nature and one is a machine.
If a naturally forming ruby absorbs some nearby chromium in the Earth's crust, you wouldn't hesitate to call it undeniably a ruby. So if a synthetic ruby absorbs a microscopic amount of tungsten from a laboratory crucible, why does it suddenly become a different class of material? In both instances, it is just a crystal lattice absorbing whatever local environment it happened to grow in.
Okay, you are equating the random varied complexity of geology with systematic mechanical engineering. And to show you why that distinction fundamentally alters the gem, let's talk about the water anomaly in synthetic emeralds.
The flux-grown emeralds.
Right. Synthetic emeralds grow in via that liquid-heavy metal flux method we just talked about, will literally not contain water.
That is correct. The high temperatures of the flux completely preclude the presence of water molecules in the crystal structure.
Think about the implications of that. Water is deeply intrinsically associated with the natural formation of mined emeralds. It is a foundational part of how they are born in the earth.
Sure.
If you engineer a creation environment so extreme and so unnatural that it completely excludes water, an element fundamental to the natural genesis of the stone, you haven't just recreated the gem in a sterile room. You've engineered an entirely new species.
A new species? Come on, just because it lacks water?
Yes, you have stripped away a foundational characteristic of the gem's historical genesis. It's an emerald in backbone only, completely lacking the vital hydration that characterizes the real, authentic material in the wild.
Wait. You view the absence of water as a loss of identity, but I view it as an isolation of the pure chemical form. This brings us to a really crucial pivot point in the source material. Natural geology is incredibly messy. It introduces all of these extraneous elements. But in a lab, utilizing pristine raw materials, we strip away the chaotic noise of the Earth's crust.
You call it noise, I call it the defining character of the gem.
But look at what happens when we use extreme purity. Laboratory-grown gems generally lack certain trace elements precisely because we don't use dirty raw materials.
Right.
Take laboratory ruby and sapphire. They are often missing or have significantly reduced levels of magnesium, titanium, vanadium, chromium, iron, and gallium compared to mined stones.
Exactly my point.
But this absence of magnesium or iron isn't a flaw. It isn't a missing piece of its identity. It is a hallmark of perfectly controlled crystallization. The laboratory is giving us the idealized, mathematically perfect form of the gemstone. It is doing what nature was trying to do, just without all the geological interference.
Oh, but that very lack of trace elements is exactly how gemologists definitively separate laboratory-grown from mined gems. Trace element chemistry is the undisputed diagnostic key for differentiation.
Right, it's how we tell them apart. I'm not denying that.
But think about what that actually means conceptually. If the absence of magnesium, titanium, and gallium is the definitive diagnostic tool for separation, if we literally rely on the absence of these elements to fundamentally classify the gem under a microscope, then on a granular scientific level, the two materials are not identical.
They're diagnostically different, yes.
Their diagnostic behavior is entirely divergent. If one stone registers a complex, varied suite of geological trace elements, and the other is a pristine blank slate missing the very signatures that characterize the material in the wild, you simply cannot claim they are the exact same entity. The mathematical purity you are praising is the exact diagnostic criteria that proves its artificiality.
I understand that tracing the absence of gallium or the presence of a crucible metal like tungsten is a highly effective diagnostic tool. It is brilliant forensics.
It really is.
But forensic separation doesn't equate to a fundamental difference in identity. Let me give you an analogy. It is akin to identifying where a car was manufactured by analyzing the microscopic dust on its tires.
Dust on the tires? Really?
Yes. Think about it. The dust or the lack of dust or the presence of highly specific synthetic factory dust tells you the exact location of the factory. It tells you the car's birthplace.
Okay.
But the dust doesn't change the make, model, or engine of the car itself. An HPHT diamond created by mimicking the crushing pressure of the Earth in a laboratory press is structurally still a diamond.
Structurally, yes.
A moissanite crystal built entirely atom by atom from a gas phase via sublimation, still moissanite. The different direct melt methods, EFG, the floating zone method, Charles-Krosky, they're merely different factories producing the exact same vehicle.
I see where you're going.
The chemical separation techniques you're talking about are incredible tools to find the birthplace, but they do not justify reclassifying the core species of the gemstone. It retains its fundamental nature regardless of the dust on its tires.
I appreciate the car analogy, I really do, but it completely falls apart when you look at the physical reality of a crystal lattice. It is not dust on the tires, though. It is nothing like that.
How is it different?
When a flux like bismuth or lead enters a growing spinel, or a refractory element like yttrium sheds into a molten vat of sapphire, it isn't just sitting on the surface like road dirt.
Well, it is integrated.
Exactly. It is integrated. It is as if the factory melted down the tools they used to build the car and forged them right into the engine block.
That's a bit dramatic.
But it's true. It is integrated into the atomic lattice of the stone itself. You cannot wash it off. You cannot separate the creation method from the final product because the creation method is literally baked into the atomic structure.
Even if the tool is forged into the engine block, to use your terms, the engine still combusts. The car still drives exactly the same way. The optical properties, the physical hardness, the way the stone interacts with light, all of the things that make a ruby remain entirely unchanged.
Unchanged to the naked eye, perhaps, but we are looking much deeper than that. Honestly, I think we have mapped the boundaries of this disagreement quite clearly today.
I agree.
The unique trace element chemistry proves that lab-grown gems are distinct entities, defined by their synthetic genesis. Whether it is the active, permanent presence of furnace refractories and heavy metal fluxes woven into their lattice, or the highly unnatural total absence of elements like water and geological trace metals, these chemical fingerprints demonstrate that laboratory-grown gems are fundamentally divergent from their natural counterparts. The process changes the product.
And my perspective remains that because the sophisticated direct melt and solution growth methods so flawlessly replicate the foundational chemical structures, whether it is the aluminum oxide of a sapphire or the complex beryllium structure of an emerald, the laboratory-grown gems are essentially identical to mined gems.
Right.
The trace elements, whether from a platinum crucible or an ancient geological iron deposit, act merely as environmental clues to their birthplace. They tell us a fascinating story about where the gem came from, but they absolutely do not redefine its fundamental identity.
It is a profound divide in how we view the material world. But despite our distinct frameworks, I think there is a really solid point of convergence here. We both acknowledge and fully agree on the underlying science.
Oh, 100%. Trace element chemistry is undeniably the most effective key method for differentiating laboratory-grown from mined gemstones. The science of separation is clear.
Exactly. The heavy metals are there, the geological dirt is absent. It is only the philosophical interpretation of that science where we diverge.
Absolutely. The mass spectrometer doesn't lie, but it leaves us with this beautiful, lingering tension. We are forced to wonder whether a gemstone is ultimately defined by the pristine, mathematically perfect realization of its raw chemical formula, or if its true identity is forever bound to the complex, imperfect, incredibly messy geological history recorded within its impurities.
That is the perfect way to frame it. For those looking to dive deeper into this, there is an incredible amount of technical nuance to explore in the material regarding the specific mechanics of direct melt growth methods, how flux lowers melting points, and how these highly controlled environments influence crystal formation at the atomic level. But we will leave the ultimate classification up to you to ponder.
Is perfection the ultimate realization of nature? Or is perfection actually the ultimate fingerprint of artificiality?
A question without a single, simple answer. Thank you for joining us for this intellectual exchange. Keep questioning, keep analyzing,
and we will see you next time.